Hi, in this video we're going to be talking about complex numbers in their trigonometric, exponential, and polar forms. In a previous video we talked about complex numbers in the rectangular form, z equals a plus bi. A was the real part of the complex number, b was the imaginary part, and I was the imaginary unit, which equals the square root of -1. We're going to start from the rectangular form and then develop a trigonometric form, an exponential form, and a polar form. You'll notice in these other three forms, instead of having an a and a b, we have r's and thetas. So if we start with our z equals a plus bi, and we draw that on the complex plane. So here is my complex number z. What I'm going to do is I'm going to create a right triangle by creating a line segment from the origin to z, and dropping a perpendicular here. So I've created this right triangle. This dimension is a. The dimension of the other leg is b. I'm going to call the hypotenuse r. And this angle with the positive x-axis I'm going to call theta. All right, so now what I need to do is I need to find substitutions for a and b that include r and theta. So we'll use a little bit of trig to do that. So if I think about cosine theta on this right triangle, cosine theta is adjacent over hypotenuse, so a over r. If I solve that for a, I get a equals r cosine theta. Now I'm going to do the same thing for sine theta. Sine theta equals opposite over hypotenuse, so b over r. Solving that for b, I get b equals r sine theta. So now I'm going to use those two substitutions up here in the rectangular form. So instead of a, I'm going to write r cosine theta. And instead of b, I'm going to write r sine theta, then I. And now all I'm going to do is I'm going to factor out the r. So I have r times the quantity cosine theta plus. Now I'm going to put my I in front of the sine theta. It's just a little less confusing that way. I sine theta. And there we have our trigonometric form for a complex number. Now, we have to find values for our r and our theta, right? So if we were actually converting a complex number in rectangular form into trigonometric form, we'd have to find some way of figuring out what r, and what theta is. So how would we do that? Well, let's look at our figure over here. And r is just going to be the square root of a squared plus b squared. So all I'm doing is using the Pythagorean theorem. We will know what a and b are, the two legs, so we can find r as the square root of a squared plus b squared using the Pythagorean theorem. Well, what about theta? Well, let's use a little more trig. So I could say the tangent of theta equals opposite over adjacent, b over a. What does that mean? Well, that means I can say theta is going to equal the inverse tangent of b over a. So when we need to do our conversions from rectangular to a trigonometric form, this is what we're going to use. So let's try an example. So I want to express z equals 4 plus 3i in trig form. So I need an r and I need a theta. So r is going to be the square root of a squared plus b squared. So the square root of 4 squared plus 3 squared. So square root of 16 plus 9, Square root of 25 is 5. Okay, so we have our r. Now, for theta, theta equals the inverse tangent of b over a. So the inverse tangent of 3 over 4, because here's our a, that's our b. And now it becomes a calculator problem. If I punch that into my calculator, I'm going to get a decimal approximation. I'll round it to 1 decimal point of 36.9 degrees. And I'm going to choose to work in degrees. So 36.9 degrees. So let's think about this theta for a minute, though. If I've got my real axis here, my imaginary axis here, then my complex number 4 plus 3i is going to be here in quadrant 1. So that 36.9 degree angle makes sense. That is a quadrant 1 angle. So we found our r and our theta. Now all we have to do is write it in trig form. So I've got z equals r, so 5, times the cosine of 36.9 degrees, and don't forget your degree symbol if you're using degrees, plus I times sine of 36.9 degrees. And there you go. That's the trig form of that complex number 4 plus 3i. Now we're going to do one more example converting from rectangular to trigonometric form, because I want to show you something that could happen. So again, we've got rectangular form. We've got our a plus bi. Our r, easy enough, square root a squared plus b squared. So the square root of -3 squared plus 5 squared. So what have I got? The square root of 9 plus 25. So I've got the square root of 34. All right, let's try our theta. Our theta, inverse tan of b over a. So the inverse tangent in this case of b is 5, a is -3, and I get approximately, when I punch this into my calculator, I approximately get -59.0 degrees to 1 decimal place. Okay, so we have to think about that angle again. So in the complex plane here, my number is -3 in the real, 5 is the imaginary. So here is my z. I'm over in quadrant 2. So my angle is actually a quadrant 2 angle, but what did I end up with? I ended up with a quadrant 4 angle. And what's going on here? Well, it's because your calculator is going to give you, if you're doing inverse tangent, it's going to give you a quadrant 1 or a quadrant 4 angle. So we had a negative value, 5 over -3, so we're going to get a 4th quadrant angle, which is not what we want. We want this quadrant 2 angle. Well, we know tangent is periodic every 180 degrees, so all I have to do to fix this problem is add 180 degrees to my -59, which leaves me with 121.0 degrees. Okay, so that's a quadrant 2 angle, so everything's good now. So in trig form, I've got z equals the square root of 34 times the quantity cosine 121 plus I times the sine of 121 degrees. Okay, so trigonometric form done. So let's talk about exponential form. So we're going to start out with the trigonometric form. It was already in terms of r and theta, as will the exponential form be. But what we're going to do is make use of something called Euler's formula. And I'm going to use this without any proof or anything. This is a very famous formula developed by a very famous mathematician, Leonhard Euler, back in the 1700s. And it says e to the I theta equals the cosine of theta plus I sine theta. Well, if I just multiply both sides of that equation by r, I get r e to the I theta equals r times the quantity cosine theta plus I sine theta. Well, what did that equal? That was a complex number in trigonometric form. So z equals r e to the I theta, and that's our exponential form. So z equals r e to the I theta is the exponential form for a complex number. Well, that gets us to our last form, which is the polar form, which is basically just a shorthand notation for the exponential form. So here was our exponential form, z equals r e to the I theta. Our polar form, we're basically making use of the r theta. We're just kind of writing it with a little bit of a shorthand. So we're writing r angle theta, and that's the polar form. So now we have four forms for talking about complex numbers. And depending on your application, some might be more convenient than others to use. So what we're going to do now is, working from polar form, we're going to convert to rectangular form. So let's take a look at this guy. So what I've done is I've shown you a couple examples here that are actually very straightforward to figure out. We could figure this out by making conversions and whatnot, but we don't have to. I want you to think about this for a minute. So if I have in polar complex number 3 angle 90 degrees. So let's think about where that lies. Okay, so 90 degrees. So 90 degrees from the positive x-axis, I'm up here, and the magnitude is 3 units, so I'm up here at 3. So this is my Z1. Right there is Z1. So knowing that, this is a very easy conversion to rectangular, right? Because what does this say? I've got 0 for my real part, and I've got 3 for my imaginary part. So, and you wouldn't actually write it that way. You would write it as 3i, but there you go. We made the conversion. Let's do this next one. 4 angle 180. All right, same idea. So starting with the positive x-axis, we'll go over 180 degrees. So we're over here now. The magnitude was 4 units. So 4 brings me over here to what would be -4 on the x-axis. So what does that mean? It means my real part is -4, and see my y value, my imaginary value is 0. So there's no imaginary part, so this is actually just the real number, -4. Okay, so those were very easy and convenient to do. Let's see if we can do something slightly more complicated. So what we're going to do now is we're going to convert z equals square root 34 angle 121 to rectangular form. Well, we have a pretty good idea of what this should end up being, but let's see if we get the right answer. So what we need to do, rectangular form, remember, is a plus bi. So I need to convert my r and my theta to an a into a b. So how am I going to do that? Well, I'm going to use the rules that we discussed earlier. And if you forget them, just draw your little right triangle, and you can recreate them very easily. But a, remember, just equaled r cosine theta. So a equals the square root of 34 times the cosine of 121 degrees, which if I pop that into my calculator, I get negative, and I'm not going to get an exact answer because this is cosine of 121 degrees, so I'm going to round to 1 decimal point, and I get 3.0 degrees. Okay, so we do the same thing for b. b equals r sine theta. So b equals square root 34 times the sine of 121 degrees. And again, this is going to be an approximate value, but it's going to approximately be 5.0. So my complex number in rectangular form is my a, whoops, I shouldn't have had a degree mark there, is 3.0 plus 5.0i. And that's what we would have expected, because that's what we started out with when we created the trig form, which also had the r of square root 34 and the theta of 121 degrees. So all of these forms represent the same complex number. All right, so in the next video, what we're going to be doing is we're going to be concentrating on polar form and using it to perform operations of with complex numbers, addition, subtraction, multiplication, and division. So that will be for our next video.